curves and regions on the Argand diagram. So before we get stuck into sketching on the Argand diagram and looking at regions, I want to look at a few useful things that's going to help us in our sketching. We know that we can define a complex number as x plus iy in Cartesian form. And this is going to help us, just this alone, when it comes to sketching. And let's get a few definitions from this. So we know the modulus of z is going to equal x minus iy. Sorry, the conjugate of z. The modulus of z is going to equal the square root of x squared plus y squared. Let's have a look at z plus the modulus of z. That's going to be x plus iy plus x minus iy. These will cancel out. We just get 2x. Let's look at z minus the conjugate of z. This will be x plus iy minus x minus iy. The x's will cancel, and minus minus iy becomes plus. So we get plus 2iy. Let's look at the modulus of z minus a plus ib. So this is in the form of some complex number z minusing another complex number. So let's sub in z as x plus iy minus a plus ib. So we're going to get the modulus. Let's group in our real terms. So we've got x minus a plus, we'll factorize out our I out of our imaginary terms, and we'll get y minus b. And the modulus of this is we just take the real part, which is x minus a, and square it, adding in the imaginary part squared, and all square rooting it. So just so far we can see that if we have the modulus of a complex number, it's going to be represented on the Argand diagram as a circle centered at the origin, because all we'd have to do is square both sides. So we get the modulus squared equals x squared plus y squared, which is a circle with radius of the modulus of z. If we were adding a complex number and its conjugate, this would just give us a straight line that had no imaginary part. And if we were subtracting a conjugate from a complex number, we'd get a straight line with no real part. If we had the modulus of a complex number minus another complex number, this gives us a circle that's centered at the point A, B. So let's have a look at a few examples. We want to sketch all the following. So A is we're going to sketch z plus the conjugate of z is less than 2. We already showed that z plus the conjugate of z equals 2x. So all of these we're going to use the fact that z is equal to x plus iy. So we're going to get 2x is less than 2. Dividing both sides by 2, we get x is less than 1. And 1 is purely real. So when we go to sketch it on our Argand diagram, we're going to have our real axis and our imaginary axis. And we just go ahead and mark 1 in on our real axis. Because it's strictly less than, we need to do a dotted line. And all the places where x is less than 1 are over here. Let's look at another example. We have the real part of z equals 4, and the imaginary part of z equals 2, and we want to sketch this on our Argand diagram. So we have our real axis and our imaginary axis in terms of z. Now, where our real part is equal to 4, that's just here. So we can sketch this line that shows that. And where our imaginary part equals 2, that's just a 2 here. And we can draw in a horizontal line showing all the values where the imaginary part is equal to 2. Let's look at 2 times the modulus of z equals z plus the conjugate of z plus 4. And we want to sketch this out. So we know the modulus of z equals the square root of x squared plus y squared. And we've already seen that z plus the conjugate of z equals 2x, and we get plus 4. We can go ahead here and see if we can figure out what kind of curve this is going to be. Let's go ahead and divide everything by 2. So we'll get the square root of x squared plus y squared equals x plus 2. Let's square both sides. So we get x squared plus y squared equals x squared plus 4x plus 4. The x squareds will cancel out. So then let's go ahead and make x the subject. So we get 4x equals y squared minus 4, and divide everything by 4. So we get x equals a quarter y squared minus 1. And this is actually going to give us a sidewards parabola. So let's see if we can sketch this out. So we have our real axis and our imaginary axis. So let's go ahead and find the x-intercept by making y equal to 0. So we get minus 1. And we can find our y-intercepts, or our imaginary intercepts, by setting x equal to 0. So if we set x equal to 0, we'll have a quarter y squared minus 1. So we'll have 1 equals a quarter y squared, times everything by 4. We'll have 4 equals y squared. Square root everything, we get y is plus or minus 2. So we know our y-intercepts are minus 2 and 2, and we can go ahead and show that curve. Let's look at some more examples. So let's look at sketching the modulus of z equals 3. We've already seen that the modulus of z just equals the square root of x squared plus y squared. This all equals 3, so we'll square both sides, and we get x squared plus y squared equals 9. And this one's relatively easy, so we can see that it just makes the equation of a circle centered at the origin with a radius of 3. So intercepting at 3, 3, minus 3, and minus 3. What about this example here? The modulus of z plus 4 plus 3i equaling 2. So let's let z equal x plus iy. We have plus 4 plus 3i, and we need the modulus of all this equaling 2. So let's group our real parts and our imaginary parts. So we're going to have x plus 4 as our real part. We'll factorize the I out and get y plus 3. And we need the modulus of all this equaling 2. Now the modulus is just going to equal the square root of our real part, x plus 4 squared, plus our imaginary part, y plus 3 squared. This equals 2, so let's square both sides. So we get x plus 4 all squared plus y plus 3 all squared equaling 4. And hopefully we can see this is just a circle, but not centered at the origin. We have our real axis and our imaginary axis. So this circle is centered at minus 4. Minus 3. Over here with a radius of 2. We get something like that. All right, let's look at another example. The modulus of z minus 4 equaling the modulus of z plus 1 minus 5i. Now, just looking at this, we've got two modulus that are equal to each other, so we're talking about distance. So that's just a bit of a clue before we see what we get. Now, if we let z equal x plus iy, we get x plus iy minus 4 modulus. Then we get x plus iy plus 1 minus 5i modulus. Let's group our real parts and imaginary parts. So we're going to have x minus 4 plus iy modulus equals x plus 1. Let's factorize out the I out of these two terms. So we'll have I outside of y minus 5 modulus. And find the modulus, we're just going to take the square root of our real part, x minus 4, all squared, plus our imaginary part squared, equals the square root of our real part squared, x plus 1 squared, plus our imaginary part squared, y minus 5 all squared. Let's square both sides. So cancel out with the square root. So the square and the square root all cancel out. Let's go ahead and expand our brackets. So we get x squared minus 8x plus 16 plus y squared equals x squared plus 2x plus 1 plus y squared minus 10y plus 25. The x squared will cancel. The y squares will also cancel. And let's bring everything together. So let's take everything to the right hand side. So plussing 8x to both sides gives us 10x. We've got our minus 10y on that side. And minusing, so we've got 1 plus 25 on this side, which is going to give us 26. And minusing 16 from 26 is going to give us 10. Divide everything by 10, we get x minus y plus 1 equals 0. Add y to the right hand side, and we get y equals x plus 1, which we know is just a straight line. So sketching this out, we know we're going to have a y-intercept of 1 and an x-intercept of -1, and we get this straight line here. But to make a bit more sense of this example, we can think about z minusing z minus 4. So thinking about the complex number 4 plus 0i, and 4 plus 0i would be somewhere here at 4. And then we can think about the other point being at -1 plus 5i. So that point being at -1 plus 5i, somewhere up here. And the equation that we've actually got describes the line that's always equidistant from those points. So always when we're always equidistant from those 2 points. All right, let's have a look at some more examples. So we want to sketch arg z equals pi on 4. So let's draw our real and imaginary axis. Now, sketching arg z equals pi on 4 is just going to look like this. It's all values of z that are going to have an argument of pi on 4, where this angle is pi on 4. This is but we know that arg 0 is undefined, and that's why we need an open circle at the origin here. What about sketching arg z is greater than or equal to minus pi on 3 and less than pi on 6? So we've got our real and imaginary axis. So this time we need to be careful because we have inequalities, and whenever we have just a strictly less than or greater than, we need a dotted line. So let's go ahead and sketch some of those in. So pi on 6 needs to be dotted because it's less than pi on 6, which is roughly here. So this is pi on 6. And minus pi on 3, we can draw in solid because it's the arg z has to be greater than or equal to minus pi on 6, which is about here, where this angle in here is minus pi on 3. And the region that defines the values between those arguments are all in between here. And we can't forget that we need an open circle at the origin because our argument's undefined there. All right, one more example. We're looking at the argument of z plus 3 minus 2i equals 2 pi on 3. So we'll draw our real and imaginary axis in. And the best way to think about ones in this form is we could rewrite it as the argument of z minus, we just factorize out a minus, and we get minus 3 plus 2i equals 2 pi on 3. Then we can go ahead and show the complex number at minus 3 plus 2i. So at minus 3 for the real part and 2 for the imaginary part. Because it's an argument, we're going to have an open circle here. And we have to imagine an argument of 2 pi on 3 from the positive x-axis. So it's going to be something like this, where the angle measured from here to here is 2 pi on 3.
you.